A project update, augmented reality for training. This is our team, Shohan and myself, Rohit. Introduction. Universal Testing Machine is a single machine used to convert almost 14 testers, that is, a tensile shear, compression, puncture, tear, and peel. The purpose of this project is to build a training tool in AR to teach new students how to use this machine for tension testing or tensile testing. So opportunity, each test has a unique fixture that must be fixed to a UTM machine to load the sample material. You can see here there are 14 fixtures and each fixture has a set of its own material and parts which has to be fixed properly and in a fixed manner so that the test can be done properly. Usually students tend to skip the procedure or interchange the order of procedure due to high permutation combination in the process. Learning the different combination and procedure is very hard and time consuming by reading the text manual. This project would be better alternative to text manual and would be teaching students very easily about how to perform these tests in an interactive manner. AR visualization things in 3D which would make the learning hands-on and practical. AR-based guidance and training is also very immersive and makes students more likely to follow instruction to the point. Objective. Primary objective is to reduce the training time and increase the effectiveness of the test conducted by new student. To create an AR application to train student to conduct tensile testing using UTM machine to avoid general procedure and human error while testing by assisted AR system. Our progress. So we observed as a professional taking the test and we also found that even he had a very well training but he missed few steps. For example, when he was placing the fixture in the upper slot, the pin was not going in. He did a repeated trials, even then it didn't go. So here he forgot to tighten or loosen the black ring around the part. So you can see it is also dangerous and it's also difficult for him to fix because he forgot to tighten or loosen the pin. So now once the part was kept down, he tried to place the pin in the part and he checked and it aligned properly, and he also checked with the holder, it aligned properly. Now you can see he's turning the black ring and now the height of the part has adjusted and now the hole aligns itself, and now the part, you can see the pin easily goes in. So after that we have to check the alignment of two fixtures. So most of the time students tend to skip this part and they directly go to fixing the sample inside the holder. So you can see this, we have to place it like this and check in the split level if the sample is aligned properly or not. Now after that we have to scroll this and we have to increase the and decrease the height, which also sometimes students tend to forget and they tend to get confused. So now after the alignment you have to place the sample inside and you have to lock it. So you can carefully see how the locking mechanism works, and we have to lock it from the bottom and the top. Most of the time students don't lock it properly, due to which the slipping happens and the results are not accurate. So you can see after fixing, we have to increase in a decrease the upper height to match and perfectly goes in. Now to scan the parts of these parts and bring it into Unity, we thought we will use iPhone lidar sensor, but it was not clear, so we used an industrial scanner, HandyScan Black, and the accuracy you can see is 0.025 mm and has particle size ranges from 0.05 to 4 mm, and volumetric accuracy is 0.020 mm. So here you can see that we use that scanner to scan the fixture's bottom part and the top part, which are the same and symmetric across the horizontal axis. So you can see that how we are scanning using the high-end laser sensor, and it after scanning, you can see we got the STL file, which is very accurate. After the we converted this STL file into OBJ file and imported inside Unity. Here you can see the ring in the previous slide, which was the ring which he forgot to type. So this is the application you can see. So first we have to look at the machine, and we have created a simulation that's a top and a bottom machine, and once we scan it, the virtual reality model pops up and aligns itself as a top and bottom, and there's an arrow which points towards a QR scanner, and after that we have to just add the QR scanner, bring the part near to the machine, and once it is near, all steps completed. It shows that all steps are completed. So finally we were planning to look something like this, which has a superimposition technique. Due to with the VR, we will superimpose and have arrows to tell the students what step has to be performed when and which has to be rotated. So you can see that primarily our prototype is working. So we are able to identify the part. Its arrow mark is pointing towards the part. We are just identifying it and we are just picking it up, and you can see here we are identifying the upper and lower part. As we got the VR target superimposed over that, we can next is find the part being shown. So we have to find the part. Once we find the part, that is a QR code on the part pops up, and we just want to place it on the table. So once it's placed, all steps completed. So we were able to reach till this point. So how has the original plan for the project evolved since April? It has evolved very well. So our we thought to use 3D objects as target using iPhone lidar technology, but it was not accurate. Therefore, we switched to QR codes. We printed QR codes, and to that we used as image target and stuck it to the parts. The QR code will act as an image target. Next time the camera gets out of focus at times and need maintain lighting condition. Design challenge: we did not have 3D models of the parts, so we had to 3D scan them.